Bismillahirrahmanirrahim. Assalamu alaikum dear students. Hope you're all fine. I'm Sada Fishwak from Department of Physics. Today I am going to deliver lecture 18, chapter 12, current electricity. Before this, let me make a review of previous lecture 17. In the previous lecture, we discussed why won't variable resistors and thermistor and its applications. Hope you have revised it. After listening to today's lecture, you would be able to understand electromotive force, sources of EMF, internal resistance of a supply, electric power. Let me start our lecture. We come to the topic electromotive force. Students, it seems that electromotive force, it's a force. It is not a force. Basically, it is energy. An external energy source is required by the most electrical circuits to move charge through the circuit. Whenever we deal with the circuit diagram, what happens if we connect any resistor, any device, and if we don't insert any source of energy, any source of current, that is a battery, then the charges are unable to move. So what is required for the charges? They require energy, which could be utilized in their motion. The circuit therefore must include a device that maintains a potential difference between 2 points in the circuit, just as a circulating fluid requires an analogous device, that is a pump. So all the time, whenever we move, we require energy. The same is the case for the charges. How charges move in the circuit? Definitely they need some energy source. For example, if we are having a pump and the pump is providing water, so with the help of this pump, water is capable of circulating, right? Because for the movement of water, it needs energy. Just as a water fountain requires a pump, an electric circuit requires a source of electromotive force to sustain a steady current. So, like in case of circulating water in all the fountains, in all the watering system, what is required? We need a pump. Pump provides energy. Similarly, for the motion of charges, charges need energy. And how energy is provided to the electric circuit? From a source. And that source of battery is known as electromotive force. Electromotive force is basically an energy which is provided to charges to move within the circuit. In an electronic circuit, there must be a device somewhere in the loop that acts like the water pump in a water fountain. Such a device which converts non-electrical energy into electrical energy is called a source of electromotive force. And abbreviation for electromotive force is EMF. Stands for electromotive force. Electromotive force is basically an energy source which is provided to the charges. This reminds us a pump which can cause water to move from a place of low gravitational potential to a place of high gravitational potential. Because when we deal with gravitational field, we all know whenever you want to move in a direction opposite to the direction of gravitational field, what is needed? We need energy. Just in the same way, when we want to move in an electric field, from lower level towards higher level, what is needed? Definitely we need energy. V means charges. In an electric field, when we want to move the charges from lower potential to higher potential, definitely charges require energy. Because for potential we use potential difference. Potential is always calculated between 2 points. One is the reference point and other is the point where the charges move. The difference in the two gives you the potential difference. Let me consider here this circuit diagram. The circuit diagram consists of a source of current, that is EMF, that is given by epsilon. Epsilon, that is E, it stands for EMF, that is the energy which is given to the charges. Charges where they move from positive towards negative. So I is giving you the direction of flow of current, and these charges when they pass through the resistor R, then there is a drop in potential. The charges lose energy, and from where they regain energy? From the source. When they gain energy, again they are capable of moving along the closed path. So in this way, whenever there is a drop in potential, whenever there is a decrease in the energy is provided by the source of battery. This is the mechanism. All right. The figure shows an EMF source epsilon considered to be a battery connected to a resistor R. It maintains its upper terminal at a higher potential. So always remember, this is the upper terminal, that is the positive terminal, is known as a higher potential, and the lower terminal, that is negative, and negative terminal is termed as a lower potential. So it is indicated by plus and negative signs. In the external circuit, positive charge carriers would be driven in the direction as shown by the arrow marked in the circuit diagram. EMF epsilon of a source is defined as the work done in carrying 1 coulomb of charge through the source. Suppose Q coulombs require an amount of work W joule to be transported through the source, then epsilon, that is EMF in volts, is given by E. E is equal to work done per unit charge. What is the unit of work done? Joule. What is the unit of charge? Coulomb. Joules per coulomb is equal to volt. So what is the unit of EMF? Volt. The potential at the ends of terminals of a battery when the circuit is open is called EMF. Circuit is open means when we disconnect the circuit, still there is an EMF, and that EMF, still there is energy, still there is voltage, and that is known as EMF. For example, students, if we are having a dry cell, it is written 1.5 volt. 1.5 volt is actually the EMF of that battery or of that cell. Even if we are not utilizing that cell in the circuit, it means when the circuit is open, it means when the circuit is disconnected, but still there is an energy which is stored in the cell, and that is known as EMF. EMF is present although if the circuit is not closed. If it is open, still it carries EMF. The unit of EMF is joules per coulomb, which is volt. 1 volt is equal to 1 joule per coulomb. There are many sources of EMF. A few examples are batteries or cells. They all convert chemical energy into electrical energy. Electrical generators All the generators, they convert mechanical energy into electrical energy. Thermocouples, they convert heat energy into electrical energy. Radiant or solar cell, they convert sunlight or solar energy directly into electrical energy. All right. In order to understand the difference between EMF and potential difference, because both of them have the same unit, that is volt, then what is the difference between them? EMF, students, it is the maximum potential difference between the two electrodes. Electrodes means terminals of the battery, of the cell, when no current is drawn from the cell, that is when the circuit is open. As I told you, that even if the circuit is open, if the circuit is disconnected, then the device still contain the maximum value of potential difference, which is known as EMF. While potential difference is the difference of potentials between any 2 points in a closed circuit. It means in order to observe potential difference, the circuit must be closed. All right, and EMF, even the circuit is not closed, if it is open, if it is disconnected, then still there is a source of energy which is known as EMF, and potential difference is only observed when the circuit is closed. EMF is independent of the resistance of the circuit. Whatever is the external resistance you are connecting, it is independent of it. While in case of potential difference, it is proportional to the resistance between the given points. Right? According to Ohm's law, I is proportional to V. So, potential difference, it depends upon resistance. It varies with the resistance, while EMF is independent of the resistance. Thirdly, the term EMF is used only for the source of EMF, the source of current, that is the battery. While potential difference is measured always between 2 points. That's why it is so called potential difference. And we all know difference could be calculated always between 2 points. Fourth, it is greater than the potential difference between any 2 points in a circuit, because this is giving you the maximum potential difference when the circuit is open, but potential difference is observed when the circuit is closed. And definitely when the circuit is closed, charges flow, and when charges flow, definitely they pass through the resistor, the potential drops. Means there is a wastage of energy. Energy is dissipated. That's why EMF is always greater than potential difference. However, potential difference is greater than EMF when the cell is being charged. Internal resistance of a supply. After discussing EMF, that is the source of battery, that is the source of energy for the charges so that they can move within the circuit. All supplies must have some internal resistance, however small. Students, while dealing with the circuit diagram, even when we are having a source of current, that is the battery, there are 2 types of resistances. One is the external resistance, which is a resistance connected in the external circuit. And here we are talking about internal resistance. This is the resistance inside the cell. When the cell is delivering no current, that is no load, the potential difference across the terminals will be equal to EMF epsilon of the cell. Yes, it is very clear. If the circuit is closed, but we are not using that energy, Load means any device. For example, in the circuit, we are not using any fan, we are not using any bulb, or we are not using any other electronic device. It means all the energy which is given by the cell is not delivering any current. That's why it's at this moment when there is no load, no use of this current, it means EMF is equal to the potential difference. When some load resistance R is connected across the terminals of the cell, the current I starts flowing in the circuit. The current causes voltage drop across internal resistance small r of the cell, so that terminal velocity V available will be less than epsilon. This we discussed previously, that when circuit is closed, even we are using a load resistance. It means when current I passes through the external resistor R, that is a load resistance, then there is a drop in the potential. There is a usage of that energy. Energy drops. All right, and when energy drops at this moment, this epsilon is greater than potential difference. Now we come to this small r, which stands for the internal resistance of the battery. For this purpose, we will split the battery in this term. While using this symbol, I told you that the bigger one is the positive terminal, the bigger bar is the positive terminal of the battery, the smaller bar is the negative terminal of the battery, but we don't consider the internal resistance of the cell. But when we consider the battery and the cell, then we have to consider the construction of the battery. Inside the battery, there are electrodes, electrolyte, and a chemical solution, chemical action takes place. Due to this, there is a resistance which appears, and that resistance is known as internal resistance. Here we have split it in this form, and the enclosure is giving you, it is providing you the battery E, and along with it there is an internal resistance of this cell, this battery, indicated by small r. The relationship between epsilon means EMF and V means potential difference can be easily established as I is equal to epsilon over R plus R. From where this equation comes? It comes from Ohm's law. We all know V is equal to I into R. All right. Instead of V, we use here the symbol of EMF, that is epsilon. Then what happens? Epsilon is equal to I into R. All right. And here there is no single R. There are two R's, and these are connected in series. How to find the equivalent of these two R's? One small, other big, because we all know how to find the equivalent resistance of the two resistors, that is the external resistor R, that is the load resistance resistor R, and the internal resistance small r. What would be the equivalent resistance? R equivalent would be equal to R plus R. All right. So eliminating for I, we use, instead of R equivalent, we use R plus R. So I is equal to epsilon over R plus R. All right. So by cross multiplication and by simplification, what we get, IR is equal to epsilon minus I into R. We have rearranged it because IR, the product of current and R from Ohm's law, is giving you the voltage V, that is the potential difference. So here in this relation, instead of IR, we write V. So V is equal to epsilon, that is EMF minus I into R, where I is the current which is passing through the circuit and small r is giving you the internal resistance of the cell. Okay, now what we do here? If we make small r is equal to 0, so make here there is no internal resistance. So when we put instead of R, when we put 0 here, so I into 0 makes the term IR 0. So what we get here? V is equal to epsilon. It means V is equal to epsilon means potential difference is equal to EMF of the battery when there is no internal resistance. But when the circuit is closed, the current moved through it experiences an associated drop in the potential equal to IR. Obviously, when the circuit is closed, then definitely I passes through the circuit, and when it passes through the load resistance R, there the potential is dropped, and that drop in potential is given by I into small r. Thus, when a current is flowing through a source, the potential difference V between the terminals of the source is V is equal to epsilon minus I into R. The potential V is called the terminal potential, which is less than the EMF because of the term IR representing the potential drop across the internal resistance R. It means that here V is less than epsilon. V means potential drop. Terminal potential difference or potential difference is less than EMF. By how much amount? By an amount given by I into R, because this much energy is dissipated when the current passes through the external resistance capital R. That's why V is less than epsilon when we deal with the closed circuit. The rate at which work is done in an electric circuit is called electric power. Okay, just like mechanical power. In case of mechanics, we deal with mechanical power. We know power is equal to rate of doing work. Similarly, electric power. Electric power means the electric work done. The rate of electric work done is known as electric power. Electric power is equal to work done in electric circuit, that is W over time, that is the rate of doing electrical work. When voltage is applied to a circuit, it causes current to flow through the resistance R in any time t. So this gives you electric power, and electric power is indicated by capital P. Clearly, work is being done in moving the charges in the circuit. Definitely, when the charges they move, we have to do work on it. And how we are doing work on it? By providing energy from the cell or the battery. This work done in moving the charges in a unit time is called electric power. The total charge Q flows in time t is given by Q is equal to I into T. Okay. As previously I told you about electric power. Power is equal to rate of doing electric work, and as we know this, we are familiar with this equation, that this gives you the definition of electric current. Electric current is known as rate of flow of charge, and from there eliminating for Q, Q is equal to I into T, where what is T? T is the time during which the charges move. And what is V? V is equal to W over Q. This is giving you the definition of potential difference, electric potential, that is work done per unit charge. Alright, so by cross multiplication what we get, W is equal to V into Q. Now we have to use this value of Q, which is equal to I into T over here. So what happens? That is the work done is equal to V into I into T, where what is I? I is the current. What is T? T is the time. And what is V? V is giving you electric potential. Now we come to electric power. As I told you, electric power is equal to rate of doing work, W over T. So here what we do, instead of W, we use the formula which we have derived, that is VIT over T. So T cancels. What we get? The electric power is equal to V into I. So this gives you and the formula for electric power, and electric power is equal to V into I. Okay, this is giving you the first formula for the electric power. We can derive more formulas for electric power. By using Ohm's law, we all know V is equal to I into R. So instead of V, when we put IR, so what happens? I into I makes it I square R. So in this way we get here second formula for the electric power, that is P is equal to I square into R. Now again use Ohm's law and use I, eliminating for I. So I would be equal to V by R. Alright, so here put the value of I. What happens? P is equal to V into what is I? I is equal to V. So V into V over R makes it V square over R. So you can see here for an electric power how many formulas we are having. The first one, that is work over time, that is VIT over T. So from there we get P is equal to VI, then we get P is equal to I square into R, and now we get here P is equal to V square over R. The above three formulas are equally valid for calculation of electric power in a DC circuit, direct current circuit. Okay. So it depends upon the data given. If V and I are given, we can make use of this formula. If only I and R is given but V is not given, then definitely in order to calculate the electric power we have to use this equation. And if in any numerical problem only V and R are given, there is no value of I which is given, so we cannot use this formula, then we have to use this formula for the calculation of electric power. Hope you all understand this. I end my lecture with the famous quotation of famous physicist Isaac Newton. I can calculate the motion of heavenly bodies, but not the madness of people. I thank you.